Let's get started. Today's class, today is November 20th. Again, we have three classes left before final exam. That is very important. And the most of the important subjects, such as the beam theory, has been kind of covered. But again, this topic is I'm sure that is new to you. So first, don't get disappointment by the way you understand. While it's a new topic, it's a natural, you don't fully understand that. Uh, but second, you need to keep reading the concept and keep make yourself exposed to that kind of problems. The beam is the structures. Uh, our whole engineering cannot avoid. So we should be able to fully understand, and then what's going on inside. Then you will be a wonderful designer of the automotive and eVTOLs and aerospace and bridge and literally everything. Now, today, last class, we covered the concept of the buckling. And always remember that buckling will happen structures under compression. And the structure under compression can get easily unstable, and the stability problem cause the buckling load. The structure will fail. This is the much more dangerous than just material failure. So that is the concept of buckling. Now, today, as chapter 14, there is a subject called energy method. The energy method is a totally new approach than just conventional, the equilibrium-based solving procedures. Energy method. The reason I have a chapter of this energy method is that the most of advanced topics on this solid mechanics or strength of material will be based on the energy method, such as a numerical method and so on. So with the full understanding of the subject we cover, additionally, it would be very nice to understand the energy method. So energy, well, energy, this word we already know, but the energy we used in this chapter is a little bit different. Let's say strain energy of a spring, where spring is the most fundamental structures, which will be very similar to the main structure we are dealing with, the bar and beam and torsion and everything. The main concept of the those structure has elastic, the deformation will be proportional to the external force. So let's again define the spring characteristic of a spring. Let's say this is a spring with a spring constant K. Now try to imagine you are applying the force from zero to certain level of a force, and you are applying that force to the spring. How do you feel that? while the spring constant by definition, P times Kx means that if you start from zero P, you would have a very small or starting from a zero X, right? P times Kx. We cannot apply P suddenly. We cannot have a, zero NP. Always we starting from zero and gradually increase to a P, right? That's the one uh, concept I like to clarify. Again, when we apply P, P means that you started from zero to that point P. So say P is 100, then there should be starting from 0, 1, 2, 3, 4, 5, 6, 7, 8, and 100, right? That is the P times equal Kx. So what we meant by the applying P means that we have a experience, we have a history of from 0 to P, 0 to 100. Uh, I just like to remind you this definition, not just the P itself. So if we plot P versus X, then again, this is the what I meant by the generally increasing from 0 to the P level. Forget about the definition of strain, but P and X, we always are starting from here, and then gradually apply, or we would reach a certain level. But keep that in mind, we have all the way to reach that point. We applied P, and by that time, we got this much X. Here, the X, so P times equal Kx. So X, of course, P divided by, the K. Okay. Okay. So the each point. So we already know that the energy is always P times force times X. Uh, this is we know that is relate to energy. So always force and certain distance. Okay. But when we define this, we should remember that the P is already there, and then apply the X, meaning that the P times X is the we applying like this, P and X. I don't need to further explain about the energy. When we have a force P and move by distance X, this is the energy, P times X, right? That's the energy. But in this case, try to pay attention that P is kept constant and then moved distance X, right? So graphically, we like to define the energy as this much, right? P times X. So please, this most fundamental, easy concept. Uh, Remember that energy is the P times X, force times the distance, right? At that time, P means that P has to be kept constant. 에너지가 힘 곱하기 거리죠. 이때 힘은 그 힘으로 계속 유지했다라는 의미를 뜻합니다. 그게 아주 중요한 컨셉이에요. P가 그 P로, 그러니까 예를 들어서 10뉴턴 times 1 메타 equal 10 뉴턴 메타. 그렇게 되죠. 이때, 이 10은, 10은 is a kept constant during this much movement. Am I right? That's uh, that's clear. So graphically, we can have a p times x, and we have x movement with a p. Then this area will represent the energy we are applying. Now back to this spring. As I said, when we say the p, okay, when we say the p cannot be constant to reach that point. That's the important. Why? Because to reach this P, we had to apply from zero and starting here. Then we would have a very small displacement and small force, and then another small force and things like that. So if we divide these things very small amount like this, and each one will be same as like that, but again this P will gradually increase along with the X. So rather than just the here, if we say the energy equal P times X will be wrong, right? Wrong. Because again, the P is not the final status. What we mean by P0 times the X0 is not the P0 times X0. This is obvious, but I just like to emphasize. The reason P0 is the gradually increased from zero to there. So we have to say incremental of dE at any point. We have to say P times dx. Okay, because that time, that status, P can be constant during this very incremental displacement. So P times dx is the energy stored during this the small deformations. This is okay, right? But this is not okay since the P has been changing. Okay, now we do know that P is gradually increasing. So P is a Kx and dx. And as usual, if we integrate from zero to the certain level here, okay, then that's the energy we like to obtain. And now 0 to x 0, okay, x0 is the final status, and kx and dx. Well, this will give us certainly kx0 scale the right. While you may Um, this is I'm sure this is not the first time you hear about the some strained energy of a spring and things like that, but the you guys often get confused by the final status uh, at certain level. Again, the energy needs to be uh, I would like to, instead of this, we need to say if kx0 and half x0 and kx0. This guy is the what? Would be the p0. Okay, this is the value of P0. So as you can see, X0, P0, and half, that's the exactly as we expected area of the triangle. Okay, this is the energy is stored in this spring when the force reach the P0 and deflection is X0. The fundamental reasoning is that the P is not constant, is gradually increasing. That's that is often confusing. So that's the one. That's the one I like to emphasize. That. Okay. Now we are applying or extending this concept to the more generic structures and the uh, let's say we have a very simple now bar. Okay, this is the bar. And this is the when we apply the P, again, P means that is starting from 0 to P. Okay, I would say P0 and 0 to P0. When we say P0 is a final status, not we cannot apply P0 suddenly, right? So this is a final status starting from 0 to P0. And then final status of deformation will be, I would say, delta zero. So from like that is exactly same as a spring. So when we apply P0 and delta zero, this guy will deflect extended this much. And then and this one can there will be a strain energy. Oh, the I need to. This is a strain energy. Okay, strain energy. Strain energy means that the all the energy are stored by the deformation. Okay, deformation or strain. That's why it's called strain energy. And here is exactly same as the spring. We have a P versus the delta, and then P and delta. There will be a linear relations like that, and then we reach the P0, and the deflection will be a delta zero. So the same concept. The P is gradually increasing, and then each strain energy for each delta. This represent a incremental strain. So same story goes to here. So the energy will be half P0 delta zero, and the P0, and we can say that what would be the P0? P0 and delta zero. I hope you remember that delta zero. Okay, I will use a different one. So P0 and delta zero, there is a relation that the EA and L. That is the relation. So we know that. Well, how do we get this one? Well, simply A comes divide by here, A P0 and E and L delta zero. So this is a stress and this is the strain. And this is the Hooke's law, the most famous stress-strain linear relations, right? So all you need to do is the starting from here and this and that. Anyhow, the P0, we put it here, then this will be half LEA and delta zero square. We know this one. Okay, so the in the bar, the strain energy stored in this bar will be this much. This is the what we meant. But now what I'm trying to say is that the if we look at very small amounts of this solid, uh, this very small and this small solid, the stress, okay, this is the area, the stress times dA will be applied as a force, right? And then deflection, this will be there will be certain displacement, delta will be strain times dx, because by definition, if this is the dx, the delta, uh, this will be the force, and this will be the delta, right? Because the strain is the delta divided by dx. Dx is the original length, and delta will be the deformation. So this is the force, and this is a delta. So what we try to do is that, okay, we apply this is a very small amount of a volume, and then what's going on? All the volume here, 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 every volume may experience a certain level of stress and strain. So we applying this concept by definition of this one, the small amount of strain will be uh, a the stress times dA and strain and dx. That's the what we were saying here. Okay, the integrations. And then, of course, there should be some half because this is the force and this is the deflection. And again, to reach this level of stress and to level of this much the deformation, this stress start from zero to this level. So we need to apply the half, right? So this one, we can say the half and sigma epsilon dA dx. What is that? dA dx is the volume. Okay. So this integration will be E will be like this. So this dE, I'm sorry, don't get confused. This dE is the volume-wise dV, not the the half of dE. This dE is the incremental load, but this dE is the small volume. So that's why we still have a half here. So force times the deformation, there should be half, and integration of the volume. Okay, integration of the volume. This is the strain energy of the structure, for example, in a body, in terms of stress and strain. Okay, that's why we have a general form. We have a sigma. This one, uh, I like to. Uh, okay, so a little bit. Let's say we have a body and we have a small volume, and this body subject to a certain condition and load, and this is the elastic body and the volume. Will be a dx, dy, and dz. And now this can be subject to this volume will subject to a sigma x, and the now we have all kinds of a load, right? This one and that, okay, that and this and okay, so this and all six component. We just consider one stress sigma x like that, sigma x, uh, and the epsilon x. Then we just observe that that will be half sigma x and epsilon x. But other component will be the same, sigma y and sigma x, okay, so y and sigma z, and so on and so on. We have all the same uh, procedures will apply, not only the tension or extension, but also shear load as well. So please keep that in mind. There is a half. The reason is that this stress is cannot be applied suddenly. The stress will reach that level, and it started. Okay, it started from zero to reach that level. So that's why we have a half year, and then integration all the volume is over this volume, and this is the strain energy of the this a elastic body. Okay, so the point is that the when this solid subject to the all different types of stress strain inside the body, and this body deform will deform like this, uh, will deform like this, right? Uh, this is a deformed body. Then there will be a strain energy of this body, and all you need to do is that we get the stress and strain here, then we get the energy. Now, why suddenly energy? Why do we get bothered to obtain the strain energy? Well, there is a very interesting uh, situation is that what this is the strain energy. And if we have variations, well, there will be another slide explaining here that, okay, sorry, here, the spring, X0, okay, X0, notice that X0 will be strain energy and P0. If we uh, derivative, well, strictly speaking, is a variation, but uh, the concept of a variation is can be very complicated. But forget about that. Strain energy in terms of P0. So this one, I would say, the like this. If we derivative of P, what do we have? We would have a P times P over K, right? So this one, as you can see that we can have a easily deflection in terms of a P. Uh, Once we have a strain energy expressed in terms of a P. Okay. So again, simply say strain energy are given in terms of a P, then we just a derivative of P, which will give us the deflection. Uh, well, sounds easy and then too obvious, right? But if the structure is complicated, this is not that. This can be very useful. Very useful. For example, let's say we have all kinds of spring, like there's one spring and there can be another spring and there can be another spring and another spring, the as complicated as you can imagine. All different K1 and K2 and K3 and K4 and something like that. Now, we apply the force P, and then how much it deflects, delta. What would this delta would be when we apply the field? It's very complicated, could be very complicated. But if we are able to get the whole energy of the whole structure in terms of the P0, then all you need to do is just the derivative of P0. This will be a delta zero. Exactly same concept as the before, but can be applied to really complicated structure. Then we can easily get the delta zero deflections. How can we extend that simple concept to this complicate? Well, there is a much more fundamental reasoning and procedure, but trust me, this is the strain energy principles. And then again, if the strain energy is a whole structure and given in terms of a P0, then we derivative of P0, this will be a delta in the direction of the P0. You need to remember that P0 is parallel to delta zero. When we apply the P0, delta deflection may be this way, right? Doesn't need to be parallel in the direction of P0, but the delta zero is always, this is the, I'm sorry, this is a little confusing here. Delta zero is always this much. So same direction as the P0, P, and this is a delta zero. Even though this is the real deformation, the deformation in the direction of a P0 is the can be calculated from this strain energy method. Well, sounds not that much useful, right? Uh, then, but this solve the whole can be applied to whole structures in general, like the wind turbine blade or airplane, you name it. This is the uh, makes the whole story. I just like to give you a motivation of this methodology. Well, CAE we didn't learn yet. Okay, CAE tools and things. Uh, all kinds of deflections, and imagine how complicated it can be to solve the all types of deflections like this. Can you do that? Well, could be really a big task. We have to, we don't know what exactly it is, but certainly there could be a sort of a load and deflections and heating here. And imagine that, okay? Every part of a structure, every part of will consist of series of a spring or all the elastic body, every point, right? This is exactly what I meant by the okay. This is exactly what I meant by the spring collection of a spring. Or you can say that you can say okay, where is that slide? Okay, this guy. This represent this is can be one of the structures we are dealing with. This is automotive and applied to an impact or any load, and then all the deflection shown as the contour like this is the deflection. How can you solve that? Well, once we have energy, then we can solve the using these principles, using this principle of this, and that's exactly what I meant. Okay, so the then of course there is a big question: how can we express the strain energy of this structure? Then now the story get the simpler and they boil down to the another problem state. How can we define the strain energy of the structure when subject to a certain load? Okay. Uh, well, that will be a study. That is the what we studied. But again, just imagine that what kind of a problem we can solve. Man, every the solid mechanics stuff, even for the automotive and impact and the electric car, gasoline car, is you name it, everything. Well, since I just mentioned here, it shows the only the automotive, but the airplane, you know, the all kinds of wing deformations and things like that. You can name it. You can solve the all the color shows that deflection and strains and then a failure. We as a designer, what we need to do is to define the shape, thickness, material. We get the stress, we got the safety, right? So we can get all kinds of airplane deformation and structures. Uh, Again, how to do that? Well, as I mentioned, we get the all the strain energy from every part. Uh, we can get the deflections, and then we can get the strain, and then we can get the stress, and we can decide whether it's a fail or not. That's the beauty of a strain energy. Oh, how can we solve that? Well, that's the next step story. You don't need to worry. You will get the very much systematic way of learning, but remember that this is the keyword. This is the key equations. Okay, so this one we already have that delta. Since we know that P is given as this, and then a derivative we would have a delta is a PL over EA. We have this equation from this. Uh, this is actually the first term of the sigma x and epsilon x at dv, and we get this and p delta and p while no delta we already know. We put it here. Well, looks like we already know the answer. No, that's not what I meant. We just have a way of expressing this strain in terms of any parameter uh, or in terms of P, that's the important. P, then all you need to do is just a derivative. Derivative, what's the physical meaning? Well, that's a different story, but this is the importance, the concept of uh, the bar. Well, same story goes to a shaft. I'd like to briefly introduce the shaft. There are more than 90% of students already learned the shaft, so that's why I skip. But I'd like to spend about the 30 minutes to cover the shaft and torsion theory today. But anyhow, the shaft, this is the stress and this is a strain, and exactly the same thing. The amount, when we apply the torque here, with respect to here, this will rotate, the angle rotate. And then the amount of rotation is the torsion length and G times P, G times GJ, torsion stiffness, and you can get this one. And even bending, well, we already know the stress and strain. And again, this one will be sigma x and epsilon x and half, and the volume we put here, we already know. The point is that if the strain energy in terms of m0, then all you need to do is a derivative, and we know that this rotation, this is the same as here. With respect to here, how much we apply moment, how much the rotate, right? Then this theta is the moment LEI. This is the equation we already know, by the way. Uh, I just like to remind you that this is the bending. When we starting the bending moment and stress, we already know these equations. See, this is the angle we rotate on the M. See, when we get to drive this one, we went through all different, the step and procedures. But again, if we are able to express the strain energy of these structures in terms of a moment, then all you need to do is derivative. You get this one. But here, we went through all different equations. But again, this that's the beauty of a strain energy. Strain energy is to if you know that you derivative and m and this is the how we get the theta. So well, you may get confused when we say the uh, okay, P, then delta. If we have a rotation here, then moment will be like this. So strain energy, if we derivative of P, there will be a delta. If the strain energy given in terms of a moment, then this will be a rotation. The torsion is the same as a bending moment because it's a torsion or this. So moment is related to a angle and force relate to a delta. In general, it is a pair. So don't get confused. This one and that mathematically and physically the same concept. This is the force and deformation. This is a force and this is a deformation. So this represent same concept of the energy. Our the pair of the deflections, deformation, and load. Okay, so there's a not much things I mean mention here, but the point here is that how we get the define the strain energy. So this will be key equations. Then uh, well this is just a very small touch of this subject, but I just want you to get start to think about the concept of strain energy, and then just the extension of all generic case, while this is the how important can be applied. Uh, okay. So that's the point. Now, I would say for those who didn't learn about the torsion, I like to go back to the torsion and the well, this it will be review of the torsion for those who already learn torsion. And the structure is called shaft, and when it's subject to a torsion, okay, so a shaft and torsion, and I'm not going to go in detail, but I just go review for you guys to get the general understanding of a general aspect of a torsion theory. Okay, let's have a 10 minutes break. This is 2:13. Okay, so let's get back to the 225. Okay, get back to 225. Okie dokie. See you soon. 자, 다시 얘기지만은 챕터 8, 샤프트 앤 토션으로 다시 돌아가겠습니다. 그, 우리 고체역학이 교수가 네명인가가 이렇게 나눠서 각자 좀 다른 패턴을 하다 보니까 또 학생 입장에서는 수업을 들어야 되고 해서 상당히 좀 혼돈스럽다라는 생각이 드는데, 어, 바람은 그냥 내가 혼자 200명, 300명 다 온라인으로 강의를 하면은 좀 컨시스턴트하게 배울 수 있지 않을까라는 생각도 하는데, 어, 뭐, 어쨌든. 그래서 analysis flow for solid mechanics 뭐 3 plus 5 plus 1 3 5 1 flow chart will still valid. Okay, don't forget. I'm not just emphasizing this at the very beginning. This will will uh, again, as I said, go to apply to any case, and force and material this and like that. Now for the torsion case, this force will be a torsion, or sometimes we call torque. 좀 뉘앙스가 많이 다르긴 합니다만은 상황에 따라서 뭐 torsion in general 그럼 토션이라는 게 뭐냐? 그러면 이제 주로 1D 스트럭처입니다. 이게 이제 빔은 옆으로 이렇게 보여지는 예가 많았죠. 빔은 옆으로 이렇게 보여지는 게 많았는데 뭐 토션도 뭐 이렇게 옆으로 해서 이렇게 지금 토션하고 이렇게 하면 밴딩 이게 똑같습니다만은 그 여러 가지 뭐 정의가 이렇게 좀 버티칼리 표현되는 경우가 많습니다. 어쨌든 자 이렇게 버티칼로 했다 해서 뭐 빔이랑 다른 거다는 건 아닙니다. 자 여기서 이런 롱 앤 슬렌더 바디입니다. 슬렌더. 슬렌더라는 게 뭐예요? 어차피 이 단면적에 비해서 길이가 매우 긴 거, 긴 구조물이죠. 여기에 이제 끝단에 이제 토션이 가해집니다. 이렇게. 그러면 이거는 당연히 이제 변형을 하겠죠. 변형이 이제 앵글 P입니다. 이러한 구조물, 그러니까 토션이 material 여기 이제 나중에 나오겠지만은 now this material we have two different types of material. One is the tension, the other one is shear. 이 경우에는 이제 어, 주로 이제 shear material property, shear stiffness가 이제 갖는 머티리얼에 토션이 가해집니다. 여기에 이제 deformation이 이제 돌아가는 각도 L입니다. 그래서 물론 이제 머티리얼 안에 이제 여러 가지 또 다른 이제 cross-sectional property will be defined and included in these relations, but again the torque or torsion applied to a certain material which has this shear stiffness and this shaft, okay, this is called shaft, will uh, be deformed as a rotation angle phi. Now, what is going on inside? Well, inside there will be an equilibrium and then there will be a stress. Now, instead of a shear on the tensile, we will have a shear stress. And then strength, instead of a tensile, we will have a shear tensile strength. And stiffness, well, I like to use the tau and gamma, while instead of a sigma and epsilon. Tau represent shear like this, and then gamma is important. Gamma is the angle change. This is mostly a confusing part. What the hell is the rotation? Well, this is the angle change. Compared to the tension, I mean extension like that, sigma, this will experience as delta or epsilon, right? So this is a deformation. In case of a shear stress, deformation is not the extension, it's a angle change. Okay, this is the angle change, gamma, and this is a gamma. Well, this is gamma 1, gamma 2. sometimes we changing the gamma 1 and gamma 2. So this is the tau and G gamma and sigma and E epsilon. So this is an extension case, most likely beam. Beam is nothing but the tension, right? But the tension and compression, and then but varying through the thickness, but the torsion is the shear stress and shear deformation. And strain again is the gamma, is the angle change, okay, angle change, and then a deformation condition. Deformation condition is that, let's say, with respect z equals 0, I mean z equals 0 here, and z equals L, we have there's a no rotation, and z equal L, there will be a certain rotation and something like that. So this will be the deformation condition. Is very important, as important as the applied torque. And the strengths, well, strengths, we do know the failure criterion. So this, the point is that all the procedures equally 3+1 flow chart will equally apply to a torsion case. So now let's define again in a very simple way to define what is a shaft. A shaft. Shaft is again this cross section L, very slender body, and then at the end we apply the torque. Well, this is like the this way. You know, this is a better way to show the rotations, right? And also like that. So this is a torque and this is L. And now imagine what will happen this guy. And to understand, I mean, the similar concept as the bar, what do you start? Well, we start as a P here, right? Well, to make it simpler, we just fix the 1 point and then define a delta here, right? This is a delta. The reason we constraint here is that we like to define this displacement with respect to this plane, right? By reaction, equilibrium will be the same, but for the convenience of the defining this delta. Same for here. When we apply torque here, there will be a reaction. So let's say we fix here, then we will have a rotations. If we define a line here, then this will rotate this much. And then we fix here, this will experience like, this is the angle, phi. So I would say phi 0. Phi, okay? So torque and phi. And imagine that this is the angle rotate, and this is the cross-section extended this much. So P and delta is a pair, and torque and phi is the another pair. You know, the concept of a force and concept of deformations. So that is the shaft. Well, same for the bending. You know, the bending, we apply the either rectangular or circular, doesn't matter. We have a certain body here. We apply the bending moment here, right? There will be a reaction. But again, exactly the same concept as the constraint, I mean the clamped, is easier to understand define the angle. So when we apply moment, this will deform this much, right? This much. And then we do know that this is the angle, theta, and this is the angle of rotation, theta, right? This is the cross sections, and this cross section remain vertical. Now is a rotate, and this rotate is the same as the center of this curvature. This is a theta, and this is a theta. So moment and theta. So moment directions and angle direction is same. So I like to emphasize that the physically is pretty much extension of a concept. This is all the force, and this is all the deformation. So with one clear understanding, it covers bar, beam, torsion. And then all the detailed procedure, pretty much the same. Okay? So the more you understanding structure, or the more you studying, and the problem can be simpler. I mean, the concept is better and easier to understand. Not just the one particular case, but this is a very generic concept, and I'm sure that this will help you to better understand. So anyhow, let's focus on this. But the procedure will be pretty much the same as a beam. Okay, this is a beam, and this is a shaft, and this is a bar. Pretty much same. Only difference between this bar and beam is that this is all the tension, right? All the tension. But we know that this tension is all the same, uniform, all the cross section. But here, different. All the tension, okay? All the tension, but it vary through the thickness. That's the big difference. Compression at the top and tension in the bottom, that varies linearly through the thickness. But remember, this is all sigma equal E epsilon. Sigma and epsilon is a vary through the thickness that causes the bending moment. But here, that's a big difference between the bar. But the common thing is that all under tensional load, tension deformation. And same here, the shaft and beam is a relatively concept is very similar. The shear stress tau equal G gamma. As you notice that sigma is the function of through the thickness, right? Through the thickness, it varies linearly. This is the same thing. This tau vary from 0 to outside. Is changing from inside to outside. And gamma, same thing. So that's the one we like to cover. That's the one we like to study to extend our concept to shaft. Okay, that's a big picture of the shaft. And now let's general. This is the definitions of the different types of a shaft. This is a solid, while solid is there's no hollow inside, and circular. And this is a solid circular. This is the circular but hollow. Hollow means that inside the empty. While this one is the most important structure in shaft, we will understand why. This is the much more important than this guy, because our outside is very effective than inside. Inside doesn't do much. It's very much similar like the bending. Let's say bending, we have a full cross section like that, but on the bending, this is not efficient. So what do? We change the H-beam or I-beam like this, and then we define the beam bending like this. Rather than this full solid, we move area to the top and bottom case. So that why? Because the strain or stress is much bigger on the top and bottom side. We do know the stress will increase like that. So inside doesn't do much. So that's why the same material we put outside rather than inside when we have a bending, right? So that's the main concept of I-beam or H-beam. Now, same for the torsion, that the inside this material doesn't do much. So it's going to be a waste of a material. So to save a material, to increase the shaft, I mean the better design the shaft, we remove or put the outside. This is a much more effective structure. And of course, depending on the cross section, we will have I'm sorry, this is the non-circular shaft, non-circular. Why there is a big difference? This is the circular, and this is a non-circular. Well, there are a lot of story behind, but the point is that when this guy is subject to a torsion, and this one, well, the very much complicate deformation in the cross section, which I mean, you don't have to worry, but in reality, we don't use a lot of this non-circular. The reason is very similar. This guy is not so much effective to support the shear load, and this is a much more. But again, this one and then thin walled. Thin walled means that this is the very much arbitrary cross section, but very thin. And this is the open. There is some slot open. So okay, so this is a definition. But again, I like to emphasize these structures. Now, as a first step of the theory, shaft is the deformation, observation of deformation. This is exactly the same concept when we learn, the bending. What did we learn? What did we start? You remember this guy? Well, we assume the rotate like this, and then this, and then epsilon x. Well, this is r, then r over y, and something like that, right? This is the starting assumptions of deformation. Strain, okay, strain is this strain. We found that this is a y. Oh, is proportional to y. So y equals 0 is here. So we notice that the strain will be like that. This is through the length of this strain. So the r plus y. I hope you remember this one, and theta, the theta. This is the after and r before deformation, delta theta. I'm sorry, this is the r theta, and so on, so on. And then what you found is that r over y. Well, there is a minus there. So anyhow, this is the deformation observation. That's what we are trying to do in torsion as well. Okay, so you may wonder why we start with a deformation. Well, structural analysis and understanding, we always try to understand the deformation first. So let's say we know this long bar, long shaft like this, and then a torsion. We like to pay attention to the small amount of the shaft. This is the one. Well, this will apply to the any section, by the way, and same thing. But for the convenience, we just take and define the 4 point A, B, C, D. and we define this section, okay? And then deformation with respect to a bottom plane, okay? With respect to a bottom plane, we assume that this is a clamp. And then we apply the torsion T. What will happen? Okay, B and C and D remain is the original position, doesn't move. Only A moves to A prime. Okay, so let's say we can define a certain not just the surface, okay? You try to understand any point inside, then this will be a U theta. We can define in a point UX, UY, and UZ displacement, but in polar coordinate, we can say UR, U theta, and UZ, R theta Z coordinate in polar coordinate. So, and here, this is a U theta. U theta, we don't have to drive that, but U theta, is it proportional to the R? This is R and R. Yes, U theta is increasing. U theta is proportional to R, very much obviously, okay? And also, U theta, this guy, U theta, U theta, and U theta. As you can see, is increasing even inside with respect to a Z. U theta is proportional Z. Even at the surface, you can see that this U theta is increasing with respect to Z and R. That's the two most important deformation, observation of deformation in torsion case. This is a proportional, but we do not know the constant. So we can say that U theta is a proportional R, proportional to Z, and there is some constant. That is the one. Looks obvious and not difficult to understand, but this is the most fundamental starting point. U theta is proportional to R, proportional to Z. This is this guy. How about the UR? When you have a torque T, this guy, will it deform like this? This is a UR, right? This is a UR. Imagine that this shaft, when we have a torsion, the radially expanded, no. There's no radial expansion, only torsion like this. Okay, so UR equals 0. That is the part of important assumption. How about the UZ? When we have a T, this guy, will it move upward? This guy will move upward like this. This is a UZ. No. This plane remains a plane and it does not extend it, does not expand in the R direction. Only rotation when subject to a torsion is so this is like this. So this three guy is the most fundamental observation, I would say, or you can say assumption in of the shaft under T. Okay, this is the we have to remind ourselves circular, okay, and shaft and under torque T. This is all you need actually. Rest of the procedure is just follow the rule, the equation. what will be, okay. I just want to summarize here. Now you can see what it means. Is a P, and this is a UR, okay, and then this is R coordinate and something like that. So U theta is the okay. We starting from here. Okay, we starting from here. Actually, the you can say that phi is that R times the phi, and phi is the increase proportional to z. So we can put it here, and then this is the one, and this is the one. Exactly the same topic as I mentioned. Okay, so u theta and this actually same, and this. Now, it's a very important observations of the shear strain. Like this is the same concept as like this. Okay, when we have a delta and when we have a dx, then how do you define the epsilon x? Well, how do we do that? Well, we delta over dx. This is the extensional strain, right? And the same for the, so this is actually the x derivative with respect to x. This is the partial differential way of expression of a strain. And the shear strain is the very similarly, this is the displacement and the z. So this is actually, I like to say like this. This is the original. This is the original. This guy is the extension. But rather than extension, this guy will change the angle. So that's the big difference between the extension and the shear. Oops. This is the, I would like to say this. So this is the angle change, right? And I could have defined the angle like this. This can change the angle, but we just had a rigid rotation so that we can make it a little simpler. So this is the angle, this is the gamma. Is similar to x, epsilon x. So if we put this one, uh, I like to follow the exactly same concept as above. Now this guy will have a ux derivative x, and ux is what? Uh, this one is proportional to the c times x. Because ux, you remember that when this one, this is a displacement, it will be function of the cx, right? So uh, this can be like this, and this is a c. C is the proportional coefficient, is nothing but the strain. Anyhow, this is the one, right? And same for here. The u theta, we already have this, and put it here, and the derivative z, and we have a cr. Uh, what is this? Well, it's nothing but pay attention to the mathematical meaning. The youth theta is like this, okay? This guy, and the z is this one. So dz youth theta. What is that? This is this distance divided by this. What is that? Angle, right? So that's the definition of gamma. And then from this observation, we got the C times R. And then all other strains are zero because of with this. So please remember, to make a long story short, gamma is the only strain and proportional to the R. This is the one. You remembered in bending, what was the epsilon x? Well, R over Y. You remember this one for the bending, right? For the bending. And this is a torsion. So Y is the cross-section, the coordinate. And what is R? R is the coordinate from center to the outside. Now here, important. Did we know the R curvature? No. At the very beginning, we didn't know. Similarly, we don't know this constant C, but we know this is a constant which we will derive later. This is R, which was obtained from equilibrium. Aha, this C will be obtained from the equilibrium. Same flow. See, this one is a bar. See, we don't know. We don't know. But this will be obtained from the equilibrium. Okay, next one, as you can see that, this is the, I would say, a small scale. And then this is the cross section, the area will deform. And this is the angle. Okay, it says shear strain. Shear stress will be applying like that. And then this is the one. I hope you remember this one. I'm trying to get the analogy. Uh, and what was 1 over R? You remember? d phi dx, right? Exactly same here, d phi dz. This one was from these relations, but gamma, aha, gamma is the d phi. D phi is this guy, okay? D phi dz times R, because d phi is this one. I know it's a little bit, this topic is new to you, but just to try to understand and generic concept flow. And so d phi dz is the angle rate, changing rate and proportional R. That is the gamma. And d phi dz is the constant. D phi dz is a constant. Okay, let's move on. Now, what is the next one? See, we always have a equilibrium. Equilibrium means the torsion T. See, we got this gamma is a d phi dz and R, and then this guy shear strain. What does it mean? Shear strain is caused by the G gamma is the tau. So this tau will distribute over the section and like this. So dph is a constant, is a proportional to R. That's the important. And then summation of this talk what will cause this one? Yes, torsion. So torsion will be tau. Tau is this guy. Tau times dA is the force, because the stress times area will give us the force. And then we need to multiply R. So R. This is the definition of a torque. And tau, we got this one. So tau times R and this, and then, the tau is a G gamma, and gamma is the R dphi dz, and put it here. This guy, put it here. Okay. I would like to magnify. And then tau is this, and then we have, okay, this is the R here. See here, there's a R there. See R here. R means that strain is proportional to R. That's first R. And second, there is another R. That's the definition of a torque T. So put it here, we have a twice of R and G and dphi dz and torque T. So dphi dg and G is the constant out of the integration. What is left? R squared dA and T. What is this? R squared dA is a definition of a polar moment of inertia. And then as a summary, dphi dz was unknown. Now we know that T over Gi is the this is the one we obtain. Okay, dphi dz is a T over GIP. Again, I like to just remind you that this is exactly same as considered we in the moment, bending moment. Remember, sigma x times y dA, and sigma x, what was that? E epsilon x. What was the epsilon x? Well, d theta dx times y. Put it here, and then E d theta dx and y square dA. E and this is a constant out of integration. E d theta dx, y square dA. What is this? This is exactly same concept as the polar moment inertia. Here is just the bending, second order moment of inertia, I, right? IZZ. Isn't it same flow, same definitions, exactly same one, right? So d theta dx was unknown, and then we got this one, the same thing. Okay, and then to make it further, we can simply get this theta zero is a TLGIP. Because this is the dphi dz can be written phi zero. Phi zero is the one we have at the top. We have a torque and we have a phi zero. So phi zero over L will be can be dphi dz. So phi zero L. Now here, what is the unknown? Unknown is the t rotation of phi zero where t applied. So phi zero is like that. Once we have a dphi dz, this one or this one, we put it back here. What do we have? Back here and back here. We got the stress. We got the stress. Isn't it simple? Same as a sigma x moment I times y. It's a torsion divided by IP, polar moment inertia times R. Isn't it same? Exactly same concept and flow. Starting from displacement, stress, strain, equilibrium, and finally we got the stress. Exactly same flow as the bending moment. Only difference now is that G, okay, this is a shear modulus G instead of a Young's modulus, and this is a IP instead of a bending moment of inertia. Okay, so it is important to solve it. What is the IP defined as a R square dA? Okay, let's obtain this one. So this one R square, what is the dA? dA is the R d theta times dr. We know that, right? So there is the okay, from R0 to R0. And now we have a R three times, and d theta is constant, so twice of p and dr, and then from what is this? 4 times r0 and 2 pi, and this is a 2 pi r04, right? If we have a ri, well, simply we will have a ri minus. Okay, this is the one we need to understand, the polar moment of inertia. Very important. So try to get the analogy between the bar and shaft, In the shaft, we apply the tick instead of in the bar, we applying the the just P and A, right? And the delta is like that, Young's modulus, and like this. And shaft, and we apply the torque T, and then instead of a cross section A, we have a IP, and the deformation instead of PLEI, we have a TL GIP. Instead of E, we have a G. Instead of a shear stress, the stress, we will have a T of R and R. And we can, of course, have a compare with the bending. We have a moment, and then we have a I, and we have a theta. We have a moment, L, E, I. And instead of G, we have a E. The sigma x, what do we have? We have a moment, and then I times Y. This is an important statement. We understand, we studied shaft. Now, bending theory get clearer than before. So we studying the shaft, it helps us to understand the bending. Understanding bending will help us to understand the shaft, and also the bar, same thing. So all three concepts in a row, together, helping us the structure more in general sense, rather than one subject separately. That's the whole point, and very important point I like to mention that. So, well, this is the applications. Say we have two shafts attached together. At the end, we have a T and T. When we have a T, we have also T here as a reaction. So equilibrium T here. So this one, we have a rotation with respect to this much, and we have a rotation with this and then to obtain this phi, we have to plus this, and then we have this one. So the whole shaft system, we have a T and phi and T and phi. This is the one we have. It's very much the same as the bar and P, or we have bending and bending. Okay, this is a rotation and rotation. Or we can have a simpler, like the spring to spring, right? The F. Isn't it same? Yes, they are all identical. The same concept. Only difference is the loading type and deformation type. Well, this is the case in shaft in parallel. Well, this is the now here the total P is the summation, but here total T torsion is needs to be added to get the total T, even though the shaft rotation is the same on the left and right. That's exactly is a P is here, or sometimes we have a parallel case. F is here. So K1, K2, we have a same delta, and then we can get the stiffness. So this is the good to review and extend. Okay. So the this is the one we can have several different, but the importantly we need to understand the stress inside structure and strain. Okay. This was the final exam 2017, long time ago. Well, this uh, I mean announcement. Okay, sorry, announcement. Uh, and like this, and then, well, long time ago. So thinner shaft is the extension of the shaft, but I will skip that one. But the main concept is exactly the same. The point I want to emphasize is that the thin or circular, as you can see that, I just like to repeat here. This phi, uh, all the stress, shear stress will be proportional to, I mean, G gamma, right? And then a gamma, and this guy is a dphi dz, and then a R. So this is well, something constant. The point is that tau is proportional to R. So if this is a solid like this, the shear stress will be very much small, as you can see that. This guy is small. Let's say this area and our area is the same. A1 and A2 is the same. But the role of the as a shaft is a huge outside. So no need to have a waste of a material inside. Okay, it's a waste of a material. So get rid of it. And then this is the one. And then this case we have a uh, uh, it's important to understand the shaft of a thin word. Okie dokie. That's what I like to cover today. Uh, just I mean, to give you the idea of a strain energy. Strain energy, the main concept is this is the fundamental principle for the complicated numerical approach. Okay, numerical approach. Uh, and then I briefly cover the torsion theory. Okay, this is a old subject I mean to cover this semester as a second course of the strength of material or solid mechanics. I know most of the subject is new to you. Even if I were you, I would be very much, uh, I mean, it would be unclear and then, something like that. But this is a first step for you guys to get into this subject. And the main point is that you have to keep thinking, okay? You have to keep thinking, and you should have always a spring, try to extend. How can you apply? How can you get the deflection? And then you have a simple beam. Always bring it, try to bend and try to twist, and then how you feel, what's going on in the structure. Okay, if you don't want to bring, well, use your arm. Try to bend. What's happening in my arm, my bone, extension, and try to twist. That's the beauty of the designing of the robotics. Robotics mimic our body and all the functions, and with understanding all the mechanics. The robotics is important to design. I mean the Well, robotics is nothing new, but the humanoid is something new. Humanoid means that, a robot like a human. And then mimic our human body. So what do they do? It's a physical human, is called physical AI. All the brain comes from the AI. Now we need a physical movement. Why? Even Hyundai, they like to use humanoid to replace human labor. You know what I'm saying? I don't need to repeat, but this is the real world. Now, when we design the robotics, lots of the mechanics. We are dealing with the solid mechanics. We need to understand all kinds of equilibrium and then force body. I don't want to go through, but this you know what I'm saying. The all sometimes a beam, sometimes a torsion, sometimes a bar. Imagine each body or each things is either bar, torsion, I mean the shaft, or beam. What else? Even sometimes compression, like the underbody. So be careful about the buckling. But anyhow, imagine you as a designer. This guy, humanoid, like to lift something. What do you need to consider? This one has the beam. This is a load, and this is the how much load. And you like to rotate, and you like to bend, you like to lift. So all the theory we cover in this solid mechanics, bar, shaft, and bending, all cover and apply to the design of a humanoid. And the old days we call biomechanics, but now is applied to the human design of a humanoid. And now it's a totally brain now is not like the old one. This is a totally new paradigm of the control system and sensor and actuators. But fundamentally, this whole structure is considered as the beam, shaft, and bar. Okay. So this will help you to understand all the whole things. Okay. While you do have all kinds of a sensor to detect what's going on. Same for the robot things. When we have a movement or something and then a bending, you would have some kind of a sensor. While in our body, we already have all sensors. And actuator is a muscle. Sensor is a nervous system. And then our brain will work as the controller or AI. Not the AI, we are human intelligence. So, but structurally, we need to understand the all the based on the this. Uh, for example, design of arm. Uh, You know what the Elon Musk says? The most difficult part of this humanoid is the your arm, I mean arm, and also the finger systems. Even one finger is the what is that? This can be a torsion, shaft, bending, beam, and also a bar. And you finger like this. So all the joint and fingers are considered as summations of all the uh, beam structures. I mean, the all the main structure we cover already here. So inside, there are lots of different A connectors. And look at that. This theta and rotation and bending. This is the subject we already cover. So again, when you study, you need to get yourself familiar with the all deformation. You don't need any other. You have yourself and try to lift, try to have a muscle exercise and try to think what's going on in my body and what kind of a force do I need to do. Uh, and also we already mentioned many times about this eVTOL. This is not the scientific story. This is the reality tomorrow. So prepare yourself. And what can you do? Well, try to make the yourself and sketch and try to imagine. And then how can we design this bar? I mean, the beam and torsion and lifting and so on. Now you have everything. I mean, fundamental knowledge. And now you can, rest of them can be found from you, and then you can do a lot. This is the paradigm changing. Again, this is the CAE, as I mentioned. Now, CAE, I would say structural analysis. See, well, this is the fluid flow, exactly same as the mechanics, but it's a fluid mechanics. We are dealing with the solid mechanics. And the so when he designed all these things, you know we should be able to use the computer to simulate. So with understanding fundamental theory, you know the energy method, and then we are able to do these things. We don't just design by looking. We design by understanding physics and all the mechanics. And then that makes us strong as an engineer. And you guys should be very happy to be an engineer. And now you can contribute and society and make yourself enjoyable and much more than the medical doctor. What they do? Well, they just sit and do every job same. Is really boring. They can be easily will be replaced by the AI intelligence and with all the sensing signals from human, and then there will be a prescription based on the knowledges. So uh, the again, you should be proud of yourself in choosing these mechanics. I mean, the mechanical engineer. Your world, you can be a really you can do a lot. Okay, okay. That's the one I like to cover today. And then I hope that you get the main message I like to deliver to you guys. Uh, okay. So, uh, well, thank you. And then I hope you enjoy uh, today and tomorrow. And then I hate to say, but we have a final exam. But get ready to enjoy your final exam. Okay. Thank you. Bye.